Okay, so this is a Tute solution for COMP3161's week 9 tutorial. So what we have to do here is we're given this term and we need to run our Dumas-Milner type inference algorithm on it in order to produce a type and hopefully a substitution to the schematic unification variables that we generate as we do the type inference process. So the way we're going to do this is just by following the rules. So I've got the rules here in my little sidebar just from the lecture slides, and we're just going to go step by step and see how all of this works. So the term I've got here is a function that, given an argument x, produces a pair containing x and x. So it's just like a pair of the same thing twice, applied to the argument 5. So overall, the result should be a pair of 5, 5. So we are going to run type inference on this. So the first thing we need to use is the apply rule right there. And the apply rule says first do type inference on the left-hand side. So our gamma here is empty because we don't have anything in our environment. Our E1 will be this function term here, and the E2 is N5. So we need to run type inference given the same environment and the term E1. So E1 is fun f.x pair x x. All right, so now what I want to do is continue to run my type inference algorithm. So there's another rule here, this one, which is our rule for functions, recfun terms. So the way it works is it says given context gamma and a recfun term, first we invent some new fresh unification variables to stand for the types of the argument and the types of the function in the new context that we use when we do type checking for the term pair xx, in this case, which is E. So I need to invent these new types, alpha 1 and alpha 2, and these stand for the types that we'll eventually infer for x and for f, respectively. And the term we're doing inference on is pair x, x. Okay, so that's the first part of the function rule. So let's continue. Now, pair xx, well, we don't have a rule for that in our slides. However, it works very much the same way as the normal typing rule would for pairs. So first we run inference on the left-hand side, then we run it on the right-hand side, and the type that we return is just the product type containing the types of the left and the right-hand side, respectively. So what we end up doing is, under the same context, x is of type alpha 1, f is of type alpha 2, infer the type of the left-hand side of the pair, which in this case is x. We do the same thing again because there's two x's there, so we have to go alpha 1, f is of type alpha 2, and the result is x. Okay, so now we need to use our rule for looking up variables. And technically that is actually this rule here. However, this rule assumes that we have a whole bunch of for alls on the front of the type, and therefore has a bunch of work to instantiate them all to fresh variables. But here, the type for x is just alpha 1. So we can just straight away say, all right, the return type here is alpha 1. And we return a substitution as well, remember, in this algorithm. So we also return an empty substitution. Okay. And the same goes for this side over here. We also return alpha 1. Very good. Okay, so now we have inferred the types of the left-hand side and the right-hand side of the pair. So we know that the pair itself will just be the type alpha 1 times alpha 1. and we take the substitutions that we got back from the left and the right hand side and union them, which is just also the empty substitution. Okay, now we have a type for the function's body. So in the recfun rule here, that tau in the recfun rule is alpha 1 times alpha 1, the type that we inferred for the function's body. So now, after we've done that inference, the recfun rule tells us to do some unification. So S in this case is the empty substitution, so all we really need to solve is the unification problem that looks like this. Alpha 2, the type that we invented for F, should be the same as alpha 1 to tau, where tau in this case is alpha 1 times alpha 1. So the easiest way to solve this unification problem and produce a unifier U is just set alpha 2 to be alpha 1 times, alpha 2 should be alpha 1 to alpha 1 times alpha 1. So we just look at this, we see that we have a type variable on the left-hand side, so we just substitute that for the right-hand side, and we get the same type on both sides. So, having unified them, we now know that alpha 2 is actually alpha 1 to alpha 1 times alpha 1, and we can return that substitution from the recfun, and the type that we return is alpha 1 to tau, which in this case is alpha 1 to alpha 1 times alpha 1. Okay, lastly, we have to deal with the application case. So we've done type inference for the first premise of the apply rule, so now we have to do type inference for the second one. And so that says, under the same empty context, do type inference on N5. Now this is just a number, so of course we know that this will return an int and an empty substitution. So now we've finished both the first and the second premise of the apply rule here, so we have one more premise to deal with. And it says that the type tau1, which is the type we inferred for the function here, alpha 1 to alpha 1 times alpha 1, should be the same as the type we inferred for the argument, int, to some new fresh variable, so beta in this case. So how can we unify these? Well, we sort of match it up structurally. We can see here that on the left-hand side of the arrow we've got int, and on the right-hand on the left-hand side over here we've got alpha 1. So therefore, we'll say alpha 1 is int in our second unifier. So u prime is alpha 1 is int, and we also match up the left-hand side of the arrow, and we can see that beta is alpha 1, which we know is int, times int. And the type that we return is just beta, with that substitution u prime applied. So the overall type is int times int, and the overall substitution we return is the union of u and u prime, the two unifiers that we've gathered throughout the entire inference process. And that's our answer.